Okay, so this will be the third lecture in the topic of CAMs. In the last couple of lectures, I motivated what is the need for a CAM follower system, which is a higher pair, which has a higher pair. We talked about the requirement of dwell in mechanical engineering, intermittent motion, and the CAM basically plays a very important role, or is a nice compact mechanism which can deliver basically dwells or intermittent motion quite readily. Although it is feasible to do this with 4 bar or 6 bar, we saw that it was not very compact design, and to do that graphically is quite painstaking. Now, the second half, the second lecture, I kind of introduced to you the various classification of cams based on the follower motion. We had a radial follower, which means that the translation axis basically coincided with the axis of rotation of the cam. Otherwise, it was called an offset follower. You had a knife edge, which is based on the contact. You had a flat face. You had a radial, a spherical. You also had an oscillating follower that I briefly introduced. Then we talked about force closure, which means that to maintain contact between the cam and the follower, I require an external force, which we usually do through a spring, or the geometry itself is designed in such a way that I maintain contact always, which is called form closure. All right, so we looked at that, and now we move a little bit forward. We want to actually design a cam for a particular requirement of follower motion. I'm going to take the example of the IC engine valve and work my way through. Please remember that the cam design is quite flexible. The following follower motion need not be the kind that I'm going to look at as an example, where I will have two valves, as you saw in the intake valve. It opens, then stays put at the open position for some crank angle rotation, then closes, and then stays put at that position for the rest of the crank rotation. So this is a two dwell scenario that you have with a valve. I'm going to take that as an example to illustrate the CAM synthesis process, but keep in mind that I can have a single dwell follower, I can have no dwell follower, I can have three dwells, whatever, there are variety of possible designs that you can come up with. So that this is only an illustrative thing. So please don't think at the end of this all follower motion will have two dwells. That's not necessary. Okay, the starting point, as I said, is basically the valve. For the follower motion has to be prescribed in order to design a cam. We'll have to come up with the follower motion for one full rotation of the cam. So we saw the IC engine valve earlier. So a four-stroke engine typically corresponds to 720 degrees of crank rotation. Remember that the camshaft will only rotate 360 degrees. So let's look at a typical valve timing diagram. This is something that people do in IC engines. What I want you to pay attention to is the green curve. This line is where the intake valve opens, which is about 15 degrees before top dead center. Top dead center is when the piston is at the top. Bottom dead center is when the piston is at the bottom. So about 15 degrees before it reaches top dead center, the intake valve opens. This is a typical valve timing diagram of a four-stroke petrol engine. And you can see that it opens and then remains open. Of course, here this is the suction part of it, and remains open till about 30 degrees past the bottom dead center. Remember, to go from top dead center to bottom dead center in a four-stroke engine is 180 degrees of crank rotation. So when the crank rotates 180 degrees, you go from top dead center to bottom dead center. So 15 degrees before that, so that is an additional 15 plus 180, which is 195. And then you have the intake valve closing completely only at 30 degrees past BDC, which means I have total of 225 degrees. So the intake valve remains open for 225 degrees of crank rotation. The cam, on the other hand, has basically rotates only through half of that, which is 112.5 degrees. And so the cam when we design the cam, we assume that it is rotating at constant speed. This is how it is designed. And we assume that it completes 360 degrees rotation while the crank rotates 70 degrees, 720 degrees. This is accomplished using gears, which you will study a little bit later. So what is called as a 1:2 gear ratio. I will show you this. I'll click on the YouTube link here. It'll open this and you can see this. We have an advertisement. Let's wait for that. Okay, skip ads. So you can see here, this is the drive. That camshaft is on top. The drive is coming from the crankshaft, which you can see here. This is the crankshaft, and from the crankshaft output through this is timing belt. So you have a 1:2 reduction that is going to be here. This is a toothed timing belt. So we transmit from here to here, and then we basically achieve the reduced speed. So when the increased speed, because 720 degrees is to 360 degrees, we are going to speed it up. So effectively, this is through a timing belt, as it is called. This timing gear, as the technical term for that. So the crankshaft, and then the top you can see the camshaft. So this is typically how we will convert 720 degrees of um, I will stop this, 720 degrees of crank rotation to 360 degrees of cam rotation. Okay, let's go back here. So um, we will see this a little bit later. The gear system, Dr. Abhijit will talk about that. So let's look at the inlet intake valve. So you know that the open to close is basically 112.5 degrees, and then after that it remains closed till the end of the cam rotation, and then again the cycle will basically repeat. So intake valve opening to intake valve closing is 225 degrees in 720 degrees of crank rotation. So since the crankshaft is rotating at half the speed of camshaft is rotating at half the speed of the crankshaft, the IVO to IVC will be 112.5 degrees of camshaft rotation. So the rest of the rotation period, the intake valve is basically in a dwell mode. So if I roughly plot this as a function of cam rotation angle, so this is how it will look. So this is the intake valve alone I'm looking at. I'm not looking at the exhaust valve, but you can have a similar diagram with these angles being a little bit different, right? So you saw in that original video that this opens rather quickly and then stays there for quite some time and then closes quickly, and then of course it remains in a dwell beyond this. So this is a typical what is called as a displacement diagram of the follower. So, or it is called as the lift of the follower, since the follower lifts. Of course, in this case you saw it moving down, that's a lift in that direction. So we say either the follower lift, or the whole diagram like this is called as a displacement diagram. So a typical diagram is drawn something like this, right? Now, what is the kind of um, um, uh, of course, I will go back and let me. So how does this rise? What is the kind of profile, displacement profile, as it goes from 0 to, I have assumed that the lift is 20 millimeters. This is just some number to deal with, and then it opens completely. So it remains at that open position for some time and then returns. Now, you could have a variety of functions. I could have a straight line, right? So I can go, let's say in this particular case, this is 0 to, I think, about 22.5 degrees. We can take whatever the rise rotation can be. So it could be a straight line, it could be a parabola, it could be a sinusoidal curve, it could be anything. So there are many possible profiles that you can fit. We will talk a little bit about that. Now, what I've done is I've assumed that in that graph that I showed you, in the picture that I showed you, I had assumed that the follower motion is simple harmonic during rise as well as return. So this can mathematically be expressed for the rise in this following form: y of theta is L sine pi by 2 into theta by theta I. You can see that when theta equal to 0, the y of theta, which is the lift or the displacement, is 0, and then when it reaches theta equal to theta I, which is the rise completion angle, we basically reach the maximum lift, which is L. And this equation is valid only within this angle 0 to theta I. Similarly, for return, Theta I is the angle of cam rotation for rise. Theta D is the angle for which it remains dwelling at one position, the topmost open position. And theta R is the return angle. So for the return, we can write this as L minus the same sign equation. So when theta equal to theta I plus theta D in this equation, you can see that this will be 0. Therefore, I will remain at L. And then when theta reaches theta I plus theta D plus theta R, I get the displacement to be 0. So this can be obtained graphically, and I will show you this construction because unlike my previous years, this time I'm going to focus more on analytical methods. If you go read Professor Malik's book or look at Norton's book, there are multiple ways to derive these things graphically. I'll just illustrate this for the case of a simple harmonic motion. How do you generate this graphically? I can, instead of writing this equation, I could actually draw the curve graphically, and I'll show you in the next few slides how to go about that. And then of course I will basically look at other kind of profiles. I said, the motion in between, the kind of line that I can draw could be a straight line, parabola, higher order polynomial, sine, cycloid. So many things are possible. So how do we choose some of these kind of profiles? We'll discuss a little bit as we go along. Now let's see how I can derive this. Instead of using this equation, suppose I know it is simple harmonic, but I want to construct that graphically. Here is what I do. So what we do is, in the graphical method, basically first of all we construct what is called as a rectangular box like this. So the horizontal part of it is the cam rotation. So you can see I start on the left side of the box, bottom horizontal line, 0 degrees. The rightmost line is basically 360 degrees. I have marked 45 degrees. Theta I is basically 45 degrees for me. So from 0 to 45 it rises. 45 to 67.5 degrees it is going to be dwelling. And then from 67.5 to 112.5 it is going to return. And then thereafter it is going to dwell. So I have kind of marked those things already, right? So I draw a rectangular box. Theta is along the horizontal, the lift is along, the displacement is of the follower is along the vertical axis. So in this case I have drawn, I will take some scale. So here 40 millimeters represents 360 degrees. So therefore every 9 degrees of cam rotation is 1 millimeter basically. So the vertical height is y of theta is 20 millimeters. So I've used a 1:1 scale. So the overall lift is 20 millimeters. So in this case, each millimeter is basically 1 millimeter of rise. So that's a 1:1 scale there. All right. The next that we do is we draw to the left of this box. We draw for, this is only for, please remember that this semicircle is drawn only for construction of simple harmonic motion. So I'm assuming both rise and return are simple harmonics so that my life is simple. So we draw a semicircle whose diameter basically is this rise. So the diameter of this semicircle is 20 millimeters, which I have taken to be the lift in my case, or L in a more general case, which is that. Then of course we have already marked theta I, which is 45, theta D, which is 67.5, and theta R, which is 112.5, right? All right. Now we divide the rise and return into n segments. I have chosen 5 segments, so every 9 degrees. So I have 5 segments here. You can see first segment, second segment, third segment, fourth segment, and finally the fifth segment. Similarly, for the return, I have 1, 2, 3, 4, and 5. So each of these I have divided into 5 segments. Therefore, what I am going to do, of course, first I will draw this semicircle with a diameter L as shown. Then the overall angle from one end to the other end is 180 degrees. I will divide this by 5. So, and if you use, for example, if I had used for 45 degrees, let us say, instead of uh, 5 segments, suppose I used every 4.5 degrees, then I will have 10 segments. So therefore I will have to divide that semicircle into 10 segments. Here I am dividing the semicircle into 5 segments. So from the center you can see each of these angles So this is 36 degrees, this will be 72 degrees, this will be 108 degrees, this will be 144, and of course the last point is 180. So the center is out here. So the angle made when I draw a line from the center to C prime, the angle with the vertical line here is 36 degrees. If I draw from here to C1 prime, that angle is 72 degrees. So every 36 degrees, which is 5 segments. So we mark those angles, join them, and this is what we get. We connect these points C prime I, C dash, C1 dash, C2 dash, C3 dash are all joined by these lines, each of which makes an angle of 36 degrees. So which is 180 by 5. Then what we do is we draw lines which basically horizontal lines passing through starting from this parallel to the horizontal axis. So you can see I have drawn these lines in red are basically going through C prime, C1 prime, C2 prime, C3 prime. Of course, the top and the bottom I have not drawn the red lines, but they are also included in this. The bottom and top of the rectangles are already drawn, so I have not drawn those particular lines. Okay, so now what do we do? The first point in is A, which is we are starting from 0, that is the rise. Then the next point is the point D is obtained by looking at the C3 dash line, which intersects with the first vertical line. So that gives me D1. So this is the first point on the what we call as the simple harmonic curve. Now the second C2 dash line intersects the second vertical line at E1, so that gives me the second point on the curve. Similarly, when I look at C1 dash intersecting with the third line, I get F1, and C prime intersecting with G with the fourth line gives me G1, and the last top line L from L, if I draw a line, of course E is the last point. So similarly, A was the last point. So effectively, if I connect, if I draw a curve through these points, I basically get that's supposed to represent the simple harmonic motion. Now I am going to leave it to you. I am not going to sit and prove this. The challenge to you is to prove that by drawing this semicircle and by constructing something like this, I get a sinusoidal curve. It is very easy to do this. Just think about it. If you don't, maybe one of you guys can post it in the forum as to why this will be part of a simple sinusoidal curve. We'll forget about simple harmonic, but the sinusoidal curve, right? So prove that when I construct like this, if I join these points, that curve is part of a sine or cosine, doesn't matter. Okay, now e to g, of course, is at well, and the return is what we are going to do is to follow the reverse process. So the top line, the intersection with the first vertical line gives me I1. So earlier the top line intersecting with the fourth line was that. Now we do phi minus I. So therefore the first line will give me I1. The second C1 prime intersection with the second line gives me J1, and so on. So again I can join this, and the rest is of course well, right? So here is the curve that I have joined. Of course I have used GeoGebra to generate all of these things. And in GeoGebra, I have been lazy. I have simply used cubic splines fit through these points. That is A, D1, E1, F1, G1, E. I got one curve. And if I do a spline fit between G, I1, J1, K1, L1, and J, I get another figure. So, of course, fortunately, in this case, I'm assuming that it is both simple harmonic like this. So, this is how you can generate graphically. Now, why do we want to generate this graphically? Will become one of the ways that you can generate is through a graphical means. You can do this. The advantage is why we want to do this is, of course, we need these displacements. So if I now go there and see corresponding to the scale 0 to L, if I pick out point D1, I can now measure what is the displacement at 9 degrees. Similarly, at 18 degrees, I can measure what is the displacement. Similarly, at 27 degrees, 36 degrees, etc. So now I will have the displacements available of the follower at these points, and based on that, I can carry out a CAM design. We will come to that subsequently. Now, what are the other possible curves? So this, I said that a lot of ways that you can join, right? So this is, of course, I have described to you simple harmonic because that is what I generated there. Some of the things I will talk about, I'm not going to get into great details. I would advise you to go read Professor Ghosh and Malik book. Very detailed discussion is there on these things. I'm just going to kind of go through these things. Uniform motion. What do we mean by uniform motion? That means we assume that the rise is at constant velocity, right? So if it is at constant velocity, the displacement is going to be linear, right? So if theta dot is sorry the y prime dy by d theta is constant, then y is basically going to be a straight line based on the slope that I have, right? So that is called uniform motion. So here we have the picture. I borrowed it from Malik's book, Goshen Malik's book. So you can see this is the ideal straight line from theta to theta array. So effectively, y of theta will be whatever the slope. So if it is, so say some m into theta by theta array, that is basically the equation for. So we had a sinusoidal equation. Now it will simply be L into theta by theta array, right? So effectively, the theta array will dictate what the slope is going to be. So when theta is 0, of course, the displacement is 0. When theta is equal to theta array, it is L. So we have L into theta by theta array. But you can see, I'll go back. The second figure basically shows what is the issue with this. Now we are saying that it is uniform velocity. So when I start, remember I am sitting here, the follower is at rest here, and then suddenly it instantly reaches this velocity. And the same problem I have at point A, it is going to be forced to come to rest suddenly from this finite velocity. So therefore, there is a jump in the velocity at those endpoints. So if you look at Malik's book, he provides saying that, okay, I will keep it uniform motion over a certain interval, and then I have these transitions. So I will smoothen the curve so that I go from finite velocity to zero velocity at those two ends. So this is possible, but that you can see the beauty of having a single equation like this, which was simply L into theta by theta array, is lost here. So now I have to write L into theta by theta array is only valid within this interval. Then I have to have one function here and one function here. So now it is broken down into three functions. So that, but that design has to be done because you want that to go from 0 to v and v to 0 in a smooth fashion. The other possibility is to have uniform acceleration or followed by deceleration. Obviously, you cannot have completely uniform acceleration because if I start from opening, then how do I come stop it, dwell it at some point? So I have to decelerate somewhere, right? So you have uniform acceleration for one portion of the rise, and then you will follow it with uniform deceleration. So this is a typical curve. The graphical construction of this profile, you can see the line that is drawn here, a parabolic, the squares are put here. I'm not going to get into the details. Again, please read Malik's book to get familiar with how to construct this graphically. So the first half, essentially for 0 to theta ri by 2, I will have uniform acceleration. So I accelerate and then I decelerate basically to arrive at point A. Okay, but the problem here is that at the start, as usual, at the start and at the end, I have uniform acceleration right from the beginning. So I go from zero acceleration to some uniform acceleration. Here I go from zero, some deceleration to zero instantaneously. So so that means the jerk is kind of discontinuous at this location. All right. The last one that I will discuss, which is called cycloidal motion. The beauty of this cycloidal motion, if you assume that the rise or return is cycloidal, the continuity of acceleration, so there are no jumps at the ends. So that's one of the preferred profiles that we want to use. Again, this is an illustration taken from Professor Malik's book. It shows how to construct the cycloidal profile of rise. What is a cycloid? Of course, cycloid is what? When you have a circle rolling along a line, if you look at the locus traced by one of the points on the circle, is basically a cycloid, right? Anyway, so So this Malik's book has details of how to construct this curve. You see a circle that is out there. I'm not again. I'm not going to get into much detail. Those who are interested can read up Malik's book and deal with this. This particular curve, there is no sorry. It says at the start end sudden, that is cut and paste issue. I will correct this. This in fact, the cycloidal motion does not have this issue. There is no sudden change in acceleration at the beginning or at the end. Of course, the second part is okay. The theory of mechanisms book for graphical construction of the displacement diagram that is described there. So please go through that. Okay, I will stop at this particular point in this lecture. What we are going to do is that we are going to look at only two. We have already seen that there are many forms of rise and return. Simple harmonic is what I started with. Then I briefly told you uniform motion, uniform acceleration, deceleration, cycloidal. Now, you could have a rise which is sinusoidal, you could have a return which is cycloidal. You can combine in various ways. All of these are possible. Generally, we won't do that, but of course, you can mix and match as you please. So that is possible. So I will stop at this location. What I'm going to come back and do in the next lecture is that we are going to look at analytically deriving. First, I will look at basically a polynomial kind of a profile. If we need a polynomial kind of rise profile, what is the kind of profile that I need to have? Remember, what I'm going to ask is that I want smooth transitions. I don't want sudden jump in velocity, sudden jump in acceleration, which means that at the beginning and at the end of the rise period, I should have zero acceleration, zero velocity. Similarly, in the return, at the beginning and the end, I should have zero acceleration, zero velocity, continuity of velocity and acceleration. So if we impose these conditions, what is the kind of curve that we will get? We will look at in the next lecture.